Hello there, Mr. Sutton here with the IM384 Part 2 homework solutions on independent and dependent probability. On this problem, we want to know if these are independent or dependent and get the probability. So we have flipping a coin, and we're just doing that 5 times. So these coin flips, since when you flip a coin, it doesn't really affect what you get on the subsequent flips, these are all going to be independent events. And in this particular situation, we're looking to see the probability of landing heads up the first 3 times and then tails the next 2. So we want 3 heads followed by 2 tails. So the probability of that first head is going to be 1 out of 2. Same thing for the next head and the third head. Now after that, the probability of getting a tail is also 1 out of 2 because that was the only other possibility. And then that second tail is also 1 out of 2. So multiplying across, we end up with 1 over 32. For this problem, we want to know if this event is independent or dependent, and then the probability. So we've got 8 shirts in a closet, and 4 of them are blue, 4 are green, and we randomly select one to wear on Monday, and then a different one on Tuesday. So we're not re-wearing the same shirt because, that would be gross. So because we're not just putting the shirt back and putting it back on Tuesday, these are dependent events. The shirt that you wear on Monday, you're not going to wear that again, so that affects what you have to choose from on Tuesday. So now we want the probability of wearing blue shirts on both days. So we have the probability then that we're looking for of blue followed by blue. So the probability of that first blue shirt, well, you have 8 total to choose from. So that's our total possibilities on the first day. And 4 of those are blue. So that's 4 out of 8 for that first day for blue. Now on the second day, on Tuesday, you've already used up a shirt. So overall, you're down to 7 shirts for the total possibilities. And you used up a blue shirt. So you don't have 4 blue shirts anymore. One of them's dirty. Now you're down to 3 blue shirts. So at this point, we're going to multiply. Before we do that, though, let's reduce. 4 over 8, we can reduce that to 1 over 2. So now multiplying across, we end up with 3 over 14. On this problem, we want to figure out if we have independent or dependent events going on, and then find a probability. So let's see here. We've got a box of chocolates. We're randomly selecting and eating 3 chocolates. So this is definitely going to be dependent events because after you eat a chocolate, it's not like you can then put it back and have a chance of selecting it on the second time around. So your first selection is going to affect your second and your third selection. Therefore, these are dependent events. So now let's get to the probabilities here. We want to figure out the probability that our first piece is chocolate, the second is white chocolate, and the third is milk. So we've got milk followed by white followed by milk for our probability. And now for the probability of the milk chocolate on the first try, well, let's see here. How many chocolates do we have overall for our total possibilities? We have 3 milk chocolates, 3 dark chocolates, and 4 white chocolates. 3 plus 3 plus 4, that gives me 10. So we're going to have something over 10 for our first probability. Now, how many milk chocolates did we start with? Well, they said 3. So we have a 3 out of 10 chance of getting a milk chocolate on that first go-around. But now, let's say that we got that milk chocolate and we ate it and it was delicious. What are our probabilities now of getting a white chocolate on the second pick? Well, you've already eaten 1 of the 10 chocolates, so you're down to 9. Because again, these are dependent events. But now, what about the milk chocolates? So, I mean, in terms of the desired possibilities, we're looking for a white chocolate this time around. You ate a milk chocolate, but you didn't eat any white chocolates yet. So there are still 4 white chocolates, which means you have a 4 out of 9 chance on that second pick. But now we come to the third pick, and we've already eaten 2 chocolates at this point. So that means you only have 8 chocolates left for the total possibilities on this one. And this is where it gets a little bit tricky. Since you already ate 1 of those initial 3 milk chocolates, you now have 2 of those left over as desirable outcomes. So let's go ahead and multiply this out. Let's actually reduce it a little bit first. So the 3 and the 9 can reduce, giving us a 1 over 3. The 4 and the 8 can reduce. There's a lot of ways you could go with this 4. I'm going to reduce it with the 8, though. And that gives me a 1 over 2 for that one. And now I also notice that I have a 2 here and a 2 here. I mean, why not just cancel those out? So what I'm left with then is a 1 in the numerator and we have 10 times 3 in the denominator, giving us 30. For this one, we want to figure out if our scenario is independent or dependent and get the probability. So in this case, we're flipping a coin twice. Since one coin flip does not affect the outcomes for another coin flip, that means that we have independent events. They can just be multiplied after we find them separately. So we're trying to find the probability of heads followed by heads. So the probability of getting heads the first time is 1/2. Same thing for the second time, and we will multiply those now to get 1/4. For this one, we're trying to figure out if we have independent or dependent events. We've got a cooler with 13 bottles of sports drinks, and we randomly grab one, give it to a friend, and grab one for ourselves. So in terms of independent versus dependent, what you grab for your friend, you can't go ahead and grab that for yourself because you already gave it to your friend. So your first selection is going to affect what you get to pick the second time around, making these dependent events. The second event depends on what you do on the first one. Now for the probability, we're trying to figure out probability that we both, you and your friend, both get lemon lime. So we're looking for lemon followed by lemon. So now let's find the probability of you picking a lemon for your friend. We have, let's see here, they said 13 bottles of sports drinks overall. So that's something over 13 for that first probability. And now of those, how many were lemon lime? Well, they said 5 were lemon lime and 8 were orange. So we have 5 over 13 for that first probability. So you pick one of these, give it to your friend, and now it's time for you to grab one for yourself. Now when you reach in there, you've already given one of these 13 to your friend, and you didn't put it back. So that means you now have 12 sports drinks to choose from. And you're looking for a lemon lime, but you already gave your friend one of these initial 5 lemon lime drinks. So that means there are now only 4 of those left that you could pick. So let's go ahead and multiply these probabilities. 4 over 12 can reduce to 1/3. So we have 5 times 1 in the numerator, so 5. And then 13 times 3 gives us 39 in the denominator. On this problem, we want to know if we have an independent or dependent series of events, and then the probability. So we have a spinner with equal chances of landing on each of the 4 numbered regions, supposedly numbered 1, 2, 3, and 4, I guess, because they didn't spell that out. And we spin it 5 times. So are these independent or dependent events? Well, whatever you spin on the first time around, it's not going to affect any of your spins after that. It's not like you use up a spot after you spin it. So that means these are independent events because the spins, they're kind of off doing their own thing. All right, so now let's talk about the probability of getting 5 ones, because they're saying each spin lands in region 1. So that's the probability we're looking for. The first time around, we have a 1 in 4 chance of landing on 1. The second time around, since these are independent events, we still have a 1 in 4 chance of landing on 1. Same thing for the third time around, and the fourth time, and the fifth time. And if we were going much more than this, I would start using exponents, but hey, we're here now. So multiplying all of these out, what does this come out to? Now, you could use a calculator. I just happen to know that this is basically 2 to the second power raised to the 5th power. So 2 to the 10th, which I just happen to know is 1024, but you could use a calculator here. So that's 1 over 1024 for our probability on this. On this problem, we're flipping a coin, and we have the first. We're talking about the probability of the first flip landing heads and the second tails. And in addition, we want to know if these are independent or dependent events. Well, let's deal with that part first. Since a coin flip, whatever you get the first time is not going to affect what you can get the second time. I mean, it's not like the coin loses a side after you land on that side. These are independent events. They're totally separate. We're just going to find them and then multiply them together, whatever they are, independently. So now we're looking for the probability of heads followed by tails. So probability of getting heads on a coin is just 1 out of 2. And then same thing for tails. So we'll multiply by another 1/2 to give us 1/4. For this one, we want to figure out if this is an independent or dependent series of events and the probability. So we've got 5 boys and 6 girls in a class, and our teacher's randomly selecting 3 different students. We're not going to keep calling on the same student to answer questions. So we want to know probability that the first student is a boy, the second is a girl, and the third is a girl. Let's start with the whole independent versus dependent thing. So the person that you call on initially, that's going to affect who you can call on the second and the third time, right? Because we're picking a different student each time. So if you call on, let's say, Billy Bob the first time, well, he's not an option for your second time around. So these are going to be dependent events because your earlier selections are going to affect your later ones. So now for the probability, again, we're looking for a boy followed by a girl and then a girl. For the probability for the boy, the overall total number of outcomes here, since we have 5 boys plus 6 girls, that's 11 students that we have to choose from that first time around. And if we're looking for a boy specifically that first time, 5 of these are going to be boys, so that's a 5 out of 11 chance. Now for the second question, well, we've already used up one of those students, can't answer again, so now we're down to 10 students to choose from. That's our total outcomes for the second pick. And this time around, we're looking at the chances of randomly picking a girl. There were 6 girls in the class, and since a girl did not answer the first question, that was a boy, there are still 6 girls available to answer the second question. So we have 6 out of 10. Now for the last question, 2 students have already answered, so we're down to 9 students who are left to answer that question. And one of the students who answered was a girl. Well, that means that the 6 girls you had for the second question is now down to 5 girls for that last question because one of them answered your second question. So there's our probability. We're going to multiply it across now. Let's first do a little reducing, though. So let's see here. A lot of ways we could go on this one. It looks like the 5 and the 10 can reduce to give us 1 over 2. We can reduce the 6 and the 9 to give us 2 over 3. And then if you're looking carefully here, the 2 that we got from reducing the 6 and the 2 from reducing the 10, those can actually also cancel while we're canceling stuff. So what's left over in the numerator now, we just have a 5. And downstairs we have an 11 times this 3 that's left over, giving us 33. On this one, we want to know if we have independent versus dependent things going on. So we've got one bag with some marbles, another bag with different marbles, and we're picking a marble from each of these bags. So before we get into probabilities, because we're picking the marbles from different bags, what we pick from one bag and what we pick from the other bag, which is what they're talking about here, a blue versus a yellow, those are coming from different bags. Those are going to be independent events because whatever you get on that first pick is not going to affect what's in the other bag for the second pick. So independent. And now talking about the probability of getting a blue marble followed by a yellow one. Well, let's look at the blue first. So for the total outcomes for your blue marble, since you're just focusing on picking from that bag that has the blue and the red marbles in it, we had 5 reds, 7 blues. That's 12 total marbles that you could pick from. And we said 7 of those are blue, so you have a 7 in 12 chance of getting a blue. Now for the yellow marble, this is a completely different bag we're choosing from, so that the total outcomes are going to be different from this. So in our bag that has the yellow and the green marbles, we had 4 greens, 7 yellows. So there are 11 total marbles to pick from the second time around, because again, it's from a different bag. And now in this bag, they said that we had 7 yellow marbles. So that's going to be a 7 out of 11 chance of getting a yellow. And there's no way to really reduce this, so we just multiply as is. We've got 7 times 7 for 49 in the numerator. And in the denominator, well, let me see here. If I had a 12 times 12, that would be 144. This is going to be 12 less than that, so that's 132. For this problem, we're playing a game involving drawing 2 numbers out of a hat. They're on pieces of paper numbered 1 through 25, and we replace the number after we draw it, which is important. We want the probability that we'll draw 3 the first time and a number greater than 10 on the second. So because I'm putting the numbers back, these are going to be independent events. What I draw on the first time has no bearing on what I'm able to draw the second time. So let's go ahead and find the probability of getting a 3 followed by a number greater than 10. So for the 3, we have 25 total pieces of paper to choose from. That's the total possibilities. And only one of those has the number 3 on it. So we have a 1 in 25 chance of getting a 3 on the first draw. Now for the second draw, there are still 25 pieces of paper because if you got that 3, you put it back in there. So we're still out of 25. Now how many numbers from 1 to 25 are bigger than 10? Well, that's 11, 12, 13, 14, so on and so forth. If you count them up, there are 15 such numbers. And so now we can just multiply straight across. Before we do that, though, let's reduce a little. 15 and one of these 25s can reduce to 3 over 5. So now multiplying, we have a 3 in the numerator, and 25 times 5 is 125 in the denominator.